Hey everyone, welcome back to MLworks. In this video, we'll write a CUDA program for matrix vector multiplication. So to perform this operation, we have to ensure that the number of columns that is present in the matrix is equal to the number of elements in the vector. So basically what will happen is every column is multiplied with the corresponding number of elements. For example, the first column with the first element, second column with the second element, and third column with the third element, as shown here. So once this operation is done, you will get your final vector. Now, when it comes to CUDA programming, there are certain sections of this operation that will run in parallel and some operations that will run in sequentially. So finally we get this result. So each of these element, right, it will be is a result of a separate thread. So for first element, you will be having one separate thread, second element separate thread, and third element separate thread. So in total, there will be 3 threads for a 3x3 matrix. So when it comes to this specific operation, this is the result of this specific operation, and the second element is the result of this specific operation. 3 is the result of this specific operation. But when you go into this specific operation, each of these operations, you will see you have to multiply with this element with all the 3, this element with all the 3, and this element with all the 3. So this is happening in sequence. So we are iterating through all these 1, 2, 3, and you are multiplying with this specific element. So this is happening in sequential order. So that's what, there will be 3 threads where you will be simultaneously running these 3 operations, but inside this you will be iterating through each of the elements and you will be getting your final result. So it will be more clear when you are trying to implement this. So now let's understand the index-based computation. So basically when you're trying to run a program in CUDA, what we do is we store the elements of the matrix in a row major order, which I mean, if you see here, this is your 3x3 matrix. So this will be stored in this format. So one after another, you will have all the rows. So row 1 is present here, row 2 is present here, row 3. So this will become a lot easier for allocating memory and such that you can move your data from one CPU to GPU. So that's why we transform it into row major order. And when it comes to the parallel aspect and the sequential aspect, all these 3 operations will be happening in parallel, but each of these smaller operations that are happening, okay, these will be in sequential order. Okay, we'll implement this and you will understand this better. So let's go and implement. So first we'll import certain statements that are required for performing IO operations and math operations. So I'll include first IO stream for IO operations, and then I'll include CMath for math operations. Then I'll define my kernel function, which is matrix vector multiplication, and this will take 3 input parameters and 1 size of the matrix or size of the vector. So if you see here, we have 3 matrices, not matrices, 3 parameters. One is A, one is X, the final result, and the size of the matrix or vector. So what I'll do here is I'll set the constant float, a pointer variable, and constant float, then X, then constant, not constant, this will be varying as we are going to multiply values here. So this will be B, and then size of the matrix, which is AN. And in the previous video, we discussed how the threads are getting generated with the help of block index, block dimension, and thread index. So let us just initialize the thread index, which is int into index is equal to block index dot x into block index block dimension dot x plus thread index dot x. So this represents the row index. So if you see here, there will be, consider it, this is the row index. So this is 0, 1, 2. So this is represented by this index. Now what we'll do is we'll set a boundary condition where this index should not be more than the size of the dimension of the matrix or vector. Because what will happen is, if the index is greater than n, then you will try to access a location where nothing is present, and it will throw out of memory access for a thread. That's why we have to put this boundary condition. So index is less than n, then you have to perform these operations. So first I'll be initializing my sum, which is 0.0 float, and then I will be iterating through the column wise operation will happen. So I'll be iterating through j. So just a second, here we have to pass the data type, so float. So int j is equal to 0, j less than n, semicolon, plus plus j. And inside this, what we have to do is, we have to ensure we access elements like this way, not like in the 2-dimension way. We have to access it in a row major order. So that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so when it comes to that, for that a formula is being used, which is sum plus is equal to, we want to accumulate the results. For example, what I mean is, so when you're iterating for the first time, this will be happening 1 into 1. In the second iteration, this specific calculation will be done. So it will be, once it is calculated, it will be stored in sum. And in the next iteration, 5 into 2, and it will be getting added to the sum variable. In the third iteration, it will be multiplied, and then you will add it to the sum variable. So that's what is happening here. So we have to access each of those elements, which is index into n plus j. So this is for accessing the elements inside the matrix row major order, and then we want to multiply with our vector, which is x j, semicolon. So if you just do it for the first time, right, consider the thread index is 0. So first thread index is 0 and n is equal to 10 plus j is equal to 0. So this will lead to a of 0, and then let's move on to since we are iterating here itself, so it will be 0 plus 1. So second will be a of 1, second element. So this is how the index gets calculated for the matrix. So it will be, if you see here, right, a of 0, a of 1, a of 2, a of 3. This is how we are getting our values for the A matrix. And xj represents this one, where this is 0, 1, 2. So this will automatically fetching the each element of the vector. So once this is done, what we have to do is, outside this loop, we have to set this B array or B vector. So what I'll put here is B, the index will be the I index, that is this index, is equal to the sum value that we get after the full iteration. So this is done. So we have written our kernel function. Now what we'll do is, we'll write our main function where we'll be moving our data from CPU to GPU, perform this specific kernel function, call these kernel functions by multiple threads, and generate index for each of those thread, and then perform this operation. So let us write that. Int main, that's it. Here first let's define the three variables. One is array, one is single dimensional array or one dimension array, the other is 2-dimension array, and another is 1-dimension array. So what I mean by that, so first let's declare it float, a pointer variable a, and a pointer variable x, a pointer variable b, semicolon. Now I will be setting the size of the matrix or the dimension of the vector. So constant int n is equal to 10, semicolon. Now I want to allocate memory for each of these variables. So what I'll do is, I'll call a is equal to, I'll get the location, I'll try to set the location for this, and specify the size of the bytes that it has to allocate. So what I'll do is float star, which is the pointer, and then malloc variable, and then we'll be sending the size. So A is your matrix, so it will be n into n into size of your floating point variable. Now we have to do the same for other variables also. So here you have x. Now x and b are your vector, not a matrix. So we can avoid n into n, and it is just n. Now let me add semicolon in each of these statement. So we have defined our variables in the CPU and allocated memory to those variables also. Now you can go ahead and add some values into each of these matrix and vector. So what I'll do is I'll iterate through I first, 0 semicolon I less than n semicolon plus plus I. Inside this I'll be iterating through j int of j is equal to 0 semicolon j less than n semicolon plus plus j. So now first thing is we want to access each of the elements inside this. We want to add some values into the specific A matrix, and then we want to add value into x, and then we want to initialize b with 0. So let me add first A is equal to, which is, we know that to how to get the each of these index, which is I into n plus j is equal to 1.0 f semicolon. So we have assigned values to this specific matrix, and it contains all the values as 1. Now here at x, here we'll be sending I is equal to 2.0 f, which is a floating point value, and b, which will be set as 0. So after the multiplication only we'll get some values present in b. So we have declared these variables, we added some values into those variables, and now what we have to do is we have to set the variables in our GPU or device. So what we do is first we declare the variables, which is float. Let me copy this line and modify it a bit. So here first d underscore a, d underscore x, and d underscore b. So this is done. Now what we have to do is again, so here we allocated the memory, right? So similarly we have to allocate memory for these variables as well. So what we have to do is CUDA malloc, and I'll be setting the memory. Here I'll be keeping it as void star ampersand, it is d underscore a semicolon, and then I'll be setting the variable. For a it is a matrix, so it is size of float. So this is done. Now so I think there might be some issue here. So CUDA malloc is fine. Let me see what is the issue here. CUDA malloc matches the argument no instance of overloaded function. So is this okay? I don't think we have to pass this void. This should be fine. So here what we'll do is for dx, then db, and here also we don't want n into n, just n is enough because these are your vectors. Now what we have to do is we just have to move our data from a, x, b into d8, dx, db. So db we don't have to send, from b we don't have to send because it is just values, right? 0.0. You don't have to do anything there. Just have to copy a and x. So what I'll do is CUDA copy, not CUDA copy, CUDA mem copy, and I'll be first taking the destination address, which is d underscore a, followed by it will be the source address, which is a, then the size that I'm looking for, which is the amount of memory that I want to pass, or amount of bytes that I want to pass, which is size of float and then the direction of the movement of the data, which is CUDA mem copy. This is host to device. So semicolon. This is done for A. Now we have to do it for X. So here I'll have X. This is dx semicolon. That's it. So this is done. Now we have moved our data to GPU also. Now what we have to do is we have to trigger the kernel function, and we want to pass the data here, and this will perform this operation in parallel. For each row there will be one thread. So if you have 10 cross 10 matrix, there will be 10 threads that is going to start, and then it will be for each thread there will be separate execution that is happening. So if you see here, right, so this part where we have multiple threads will be generated simultaneously based on the index, and inside that thread you will have this operation that is running in sequence, which we are iterating. So that's the point. And now let us define what we have to do, right? First we have to set the global, we have to set the grid and then block size, and then make a call to the kernel function. So this will be the kernel configuration. So first is int block size is equal to, we can directly set it as 256, and then we can set the grid size as int grid size is equal to, the basic formula is n divided by it will be the block size, because it has to be less than, right, the number of grids will be less than this one number of elements that you are having in the vector, so it has to be less than that. So what we'll do is, first I'll be setting this as integer, and then ceiling function, inside that I'll be turning this into float. So this will ensure that the final value that we get is an integer, and in this case it will be 1. So we have defined the kernel configuration. Now we have to make a call to our matrix vector multiplication, and this is the way to make a call. First we have to pass the grid size and then the block size. So once this is done, then inside this we have to pass the data, which is d underscore a, d underscore x, and d underscore b, which is just a memory location that we are passing. We don't have any data inside it. And then we send the size of the matrix or vector, which is en, and close it out here. So this will perform the operation in parallel for each element that we find at the end of the result, right, that we do. So for each of them you will get corresponding thread. Now what we have to do is, once this is done, we have to ensure that we synchronize the device, CUDA device. So here this is the statement for that, CUDA device synchronization. So what it will do is, it will wait for all the operations to happen inside this CUDA device, and then we synchronize the results, and then only you can perform any other operation. So if you see here, right, now the results are stored in DB. Now we have to move from DB to B. So what we have to do is just copy this CUDA mem copy, and instead of you have it here, it's x d underscore b, and here you will have b. And instead of host to device, you have device to host. So this is the one. Now this is done. Now what we have to do is, we can free the memory that we have allocated here by using CUDA free. So here d underscore a semicolon, copy this, now dx, then db. Now everything is done. Now just we have to copy the results and see the results. So we have copied the results, sorry. So we have copied the result, we just have to see the results. So to view the results, we can add the print statements. So for loop, first int I is equal to 0 semicolon, I less than n semicolon plus plus I. Then we have to print, then cout. Then we have to just get the output for each of the elements that is stored in B. So I'll just Let's add some spacing between the elements. Now what we can do is we can copy this and do it for A and B also, A, B and X. So we have already done for B. So let me just do it for A now. So A is a matrix, so it will be A into N, yeah. So this will be the size we have to iterate through. This is X. Now what I'll do is I'll add a print F. So here I'll add a new line, and similarly for here new line, add semicolon and semicolon here. So we are almost done now. So what we have done is we have performed the matrix multiplication in GPU and moved the data or the final result to B array, and then we can view the results with the help of this print statements, and we are freeing the memory for the CUDA here. So let us run and compile this program with the CUDA compiler, which is NVCC. So NVCC, and this is matrix. This is day 3 folder, I guess. First we have to get to the folder, and then we have to run NVCC and matx. Right, then output will be stored in a file which is mat_vec_multiplication. That's it. So it is stored there. Now what we can do is just we can view the file once the calculation is done. So it is undergoing that parallel operation now. We'll see the results in this file. So it got executed. Now we can view the results, which is ./mat_vec_multiply. So let me expand this. So it is just giving 1 1 1 1 1. It is not showing the results. So why it is? So okay, it is new line. It is a new line. Okay. Now let us see how this is, why this is not working. So we have dA dx. Okay, is that correct? Yeah, A, B, AX, B. Then we have the size. And here we are moving the data from A to dA, X to dx. So that is happening here. So let me run this again now. Let us view the results. So yes, now it is running properly. Let us see the results. So you are noticing right here you have totally around 100 elements which are 1. Then you have a vector of 2. So what is happening is you are multiplying all these vectors 2 into 1, 2 into 1, 2 into 1, and then you are adding it together. So our first 10 elements gets multiplied by 2, and then it is added, so you get 20. Similarly for next 10 elements, next 10, and you will get a vector of 20s. Okay, so that's how it is running in the backend. So with that, I'll be concluding this video. Thank you for watching.